Okay. Oh, wait a moment. Oh, hi everyone. My name is yuting, and I am a master student in Tsinghua University. And my topic is about neutrino parametric resonance in periodic density profile. And my advisor is Mengru Wu from Academic Sinica Institute of Physics. And another advisor is Po Yan Chen from Tsinghua University. So here is my outline. My outline will be covered by 5 sections. The first one is parametric resonance. I will do a brief introduction for the parametric resonance. And the second one is one of our findings, the phase effect and the self-interference. The third one is the asymmetry shape of frequency response, a kind of weird shape we have observed by numerical simulation. And the fourth one is the shift of resonant frequency. As we can imagine, the resonance may occur in some specific frequency. However, by considering some perturbation, the resonance frequency will be shifted a little bit, and we have tried to derive it analytically and do some numerical simulation to find the shift. And the last one is the general form and the possible insight, because we have based on 2 papers and they are leave the neutrino propagate in the specific density profile like sinusoidal profile and the step function profile. So at the end, I will try to derive the general form could be applied into any density profile. So above is my tomorrow outline. First, let me talk about neutrino oscillation. This is the Hamiltonian term, and the F means the basis is in flavor space. And in this term, we could observe the omega V. This V is mean the neutrino is oscillating in vacuum with this mixing angle theta V in this mixing angle. So in this plot, we could observe the oscillating behavior of neutrino propagating in vacuum. So the horizontal axis is the space. So the unit is determined by omega n. Here's omega n related to the energy of neutrino. So we use this specific unit here. But the meaning of the horizontal axis is the space. So it's like from zero, the position generate the neutrino. So the neutrino will propagate into the vacuum, into the space, and the vertical axis is probability. So actually, the neutrino is oscillating between the probability from 0 to 1. 1 means 100%. So this is the neutrino oscillation in vacuum. However, if we consider the more interaction, like we could add this extra term in Hamiltonian. By considering this Feynman diagram, the electron and the neutrino will have some interaction. So the lambda 0 here means the density of the matter. If we can enhance the density of the matter, the neutrino oscillation behavior will be enhanced too. As we could observe, I put this lambda 0 into this specific value, 0.5. So the probability will oscillate it to the higher position. Okay, so the first resonance is coming from when the matter density, the mean density is equal to this specific value, NSW density. The neutrino oscillation will achieve the resonance. So this is the classical NSW resonance in the previous work, NSW resonance. So the next slide, I will introduce the parametric resonance. Actually, the interesting thing is here. NSW refers to three scientists, and the S is a physicist called Chernoff, and Chernoff have developed another type of neutrino resonance, is the parametric resonance. Parametric resonance is coming from the extra term. If the matter density is not a constant value, or that the matter is fluctuating, like in this case, this matter is fluctuating with the k frequency. So if we could modulate the frequency, we could also observe how the behavior change with the frequency k. Now the k is equal to 2 by the unit of the energy of neutrino. So if we modulate the frequency of fluctuating matter into another value like this, and then if we could put the modulate the frequency to another value, we could observe a little bit difference, like a wave packet. And then if the frequency could match the specific value in this place, we could guess if the k is equal to 1 omega n here, the energy of neutrino, the oscillation will achieve the resonance point here. So it's a little like the probability is accumulated when the neutrino propagate in the space. So we call this phenomena parametric resonance. And the second part, I would like to introduce the phase effect and self-interference. Because in this paper by Lamar, he had derived the original Hamiltonian in this form by some correlating approximation. In this perspective, we could observe the off-diagonal term is time dependent. So they could use this form to argue in which kind of k could make the resonance happen. However, how about the phase term here? In Lamar's paper, they made a conclusion. They said phase term is independent on the resonance criteria. However, when we do the numerical simulation, we found an interesting thing. We just changed the phase term from 0 to 2 pi. We have observed the neutrino oscillation behavior is changed with the phase term. So the phase effect should be happen in the neutrino parametric resonance behavior. And if we could plot another graph about the horizontal axis is for the k, or said the frequency of the fluctuating matter. So we could observe evidently here, if k is equal to 1, sorry, the unit is the same, the energy of neutrino. Here is the resonance. However, if I sure, yeah, yeah, but I get the amplitude of this oscillation. A little like this. I could show you the last plot, because as you can see, the plot is like this. The probability is accumulated with the space. So I just get a point in this propagating process. Yeah. Yeah. Oh, you mean this figure? Actually, this this neutrino is propagating with time or with space. So the value here is containing the information. He is isolating with time and propagating in space. So I just get the largest point for the amplitude. Yeah. Thank you. Okay, so we could observe the frequency response here. The phase would totally change the shape of the frequency response. So it is really it contradicts to the previous work or the conclusion by Lama. And now I have done another numerical simulation. The first one is the Hamiltonian in flavor space, and the method invented by Lama or other physics coming from the Rabi oscillation. They try to transform the flavor Hamiltonian into another Hamiltonian like the Rabi oscillation. So the process is like this is the original flavor Hamiltonian, and then they transform into mass eigenstate, and then they use the technical method called Rabi oscillation or wave approximation, rotating wave approximation to this Hamiltonian. So they could observe the form is like Rabi oscillation. And in this corner, this plot is I try to do the numerical simulation for the first one, the flavor Hamiltonian, and the last one, the rotating mass eigenstate Hamiltonian. First, we could, yeah. Oh, okay, thank you. The delta is coming from the transformation of basis. They do the transformation called rotating wave approximation, and the purpose is to make all the time dependent term into the off diagonal term. As you can see, in the original mass eigenstate, the time dependent term is live into diagonal term and off diagonal term. So after using this method, all the time-dependent term will live into off-diagonal term. Yeah. An advantage is they could use this because this form is similar to Rabi oscillation. So we know the condition of Rabi resonance is when the off-diagonal term, the frequency here on the exponential term, the frequency here, yeah. Oh, I have put the equation in the backup, but in the brief introduction, Rabi oscillation is a two-level oscillation. So it could be similar to this two-level neutrino oscillation here. And based on the derivation of Rabi oscillation, the resonance condition is when the frequency here equal to the value in diagonal term. This is the resonance condition of Rabi Rabi oscillation. Yeah, yeah. I'm sorry. Yeah, yeah, yeah. Okay, the plot, we could observe the, sorry, I will put the plot to, oh, yeah, it's my fault. I'm sorry. I should put this plot. Okay, I will explain more at the end. Thank you. Okay, so back to this plot. The numerical simulation is about the flavor Hamiltonian, the blue one and the green one. and they are changed with the phase term here. So we could observe if we do the numerical simulation in flavor space, the oscillating behavior will change with the phase term. However, if I just directly do the numerical simulation for this mass eigenstate, like Llama have done, the orange one and the red one, it is not changed with phase. So I could understand the reason why they make this conclusion. So the right plot is I try to add more mode into this delta lambda. If I just add one mode, okay, it almost achieves the resonance. And if I add another off resonance mode, it will be suppressed. However, even though the suppressed effect cannot be affected by the change of phase difference, so if we do the simulation in this mass eigenstate tilde basis, we cannot observe the phase effect. This is the initial conclusion. However, I found an interesting thing. Because of the initial condition, if we change the initial condition in this place, the initial condition 1, 0 means we have two bases, and initially all the state, all the component is collapsed into this one, and another one is 0. So this is a pure state. So in this pure state, the orange one and the red one cannot change with phase. However, if I just change the initial condition to the specific component here, and then we could observe the numerical result. The orange line and the red line will change with it. So actually, the reason why I should change the initial condition is coming from the basis, the change of basis. Actually, initially, we use the basis of flavor, and the flavor could be pure because it is generated by beta decay or other nuclear reaction. However, when doing the coordinate transformation, the initial condition will mix together. So this is the reason why we must do the mixing initial condition here, and then it will be consistent. Like no matter the basis is in like this blue one and this green one in flavor basis, or the basis is in mass eigenstate, they have the same behavior with the changing of phase. So this is the phase effect. And then I will derive the analytical form of the phase effect here. Actually, when considering the mixing initial condition, the probability will include this term. We call it interference term. In Llama's research, they may just consider the pure initial condition. So their numerical result just show the first one, or the second one. And now if we put the initial condition mixed together, we will get another term, another interference term here. So I will do another numerical solution to show it the detail. Because we have discussed about the resonance, actually the resonance could occur when k equal to omega n, or k equal to omega n over 2 and over any integer. Yeah, so this is the resonance criteria have been derived by Llama. And then what I do is let's focus on this second resonance Hamiltonian. The diagonal term is omega n. And we can focus on the off-diagonal term. The off-diagonal term get many, we call it Rabi modes. First Rabi mode, second Rabi mode, third Rabi mode. And if one of the Rabi modes frequency match the diagonal term, the resonance will occur. This is their criteria. The resonance will occur by some specific Rabi mode frequency match the diagonal term here. So we could observe in second resonance, the second Rabi mode could make the resonance happen. However, if I do the stimulation here, what I do is to put the third Rabi mode first. I just put third Rabi mode, so we will observe the origin line. Here is no any resonance. But after I put the second Rabi mode into this Hamiltonian, oh, the green one will achieve the resonance. However, to complete the whole scenario, I should put another remaining Rabi mode. So I put n equal to 1 this term. I put this term into here. So put this term, this Rabi mode suppress the second resonance. It suppress it. So if I put another Rabi mode minus 1 here, it will suppress, and could fit the numerical result. So we believe the existence of the suppression effect. The same thing could be observed in third resonance here. So it's like initially we put third Rabi mode, the orange one, and then we could observe the orange one could achieve the resonance. And then we put the second Rabi mode here. The second Rabi mode is green one. We put, oh, the second Rabi mode cannot suppress the third one. However, if we put the first Rabi mode n equal to 1 here, we could observe totally suppressed, almost. And then we put another Rabi mode here, it will suppress to achieve the numerical result. So this is the suppressing effect here. So above is the phase effect and self-interference. We call it self-interference is because the suppression is coming from itself. And let me explain again here. Actually, there are infinite Rabi mode here, but the infinite is coming from the rotating transformation. If we do the rotating transformation, we will make only single Fourier mode into infinite Rabi mode. So actually, the infinite Rabi mode consists of could be combined into the one single Fourier mode, the matter fluctuating. So I give it a nickname, the self-interference. And now we will do the more analytical solution for the asymmetry shape of the frequency response. We could observe the simulation here. This first one is k equal to 0.5. This is from 1/2, so we call it second resonance. And this is k equal to 1. This is the first resonance. And this one is k equal to 1/3. We call it third resonance. And then we have an interesting observation. We just change the phase simultaneously. And then we focus on the first resonance. The cycle of the phase effect is 0 to 2 pi. However, from 0 to 2 pi, we move to the left one, the second resonance. The cycle of the second resonance is 0 to pi. And then we could observe the behavior for the third resonance and evaluate it with the changing phase. Apparently, the cycle is 2 pi over 3. So we have the confidence to say the behavior of phase is determined by the N resonance, first resonance, second resonance, or third resonance, it have strong connection. The reason is here. We could observe this left plot. This is the frequency response. And then we could observe when phase is equal to 0 for phase first resonance. And then we increase the phase. The shape, this corner is be more smooth. And then when phase equal to pi, oh, it be that. But for another side, the change of the shape is in another direction. And actually, everything is coming from this interference term we have discussed, the interference term, because we could observe the phase term is living into this interference term. So after deriving the analytical form, we found that the analytical form have one asymmetry term and another symmetry term. This is the reason why the shape have this, we could focus on the green one, have this asymmetry, green one. But if the phase is equal to 1.5 pi, the blue one, it is symmetry. So actually, if the phase is equal to 0.5 pi, we could observe here, oh, if phase is equal to 0.5 pi, this term would be got rid of, would cancel. So what they leave just the symmetry term. So this is the reason why in some phase the frequency response would be totally symmetric here. So the same thing could be observed in the second resonance. We could observe here the green one and the orange one. They are the same shape. This is because for the second resonance, the N is equal to 2. So when the phase turn is 0 or pi, they will be the same if N is equal to 2. So this form could explain the behavior of phase effect. It is an interference term. Okay, and the fourth section is about the shift of resonance frequency. Let me introduce the left plot first. The blue one is by the single Fourier mode, a cosine, and we could observe the behavior here. The blue one, the behavior is the resonance will occur in 1 or 1 over 2 or 1 over 3. And it is similar when we replace the Fourier mode with step function, a step periodical step function. The resonance could occur in the same place. And one of the interesting things is the step function for another resonance, like this second resonance or this third resonance. They have no suppression. They cannot be suppressed. They have no the phenomena I have mentioned, the self-interference. So that is an interesting thing for step function. And in this plot, we have tried to change the phase again. The three colors, blue, orange, and green, refers to different phase, like here, blue, green, and orange. Apparently, the frequency response, the shape, is depending on the phase. However, for the step function, these three colors is combined together in this weird color. So actually, the step function is independent on the phase. So this is the first glance of the interesting thing for the step function. But another interesting thing we like, yeah, yeah, right. Um, and the you mean the meaning of phase in step function, right? Yeah. Um, Actually, in this case, the the phase in the step function or the time dependent is it means the position of the step function. As you can imagine, the step function is one step and oh, okay. Oh, actually, this plot is just the numerical simulation. So, oh, let me back to the slide. Do you? Sorry, yeah, one page earlier. Okay. Oh, actually, this infinite Rabi mode is derived from single Fourier mode because of the Jacobi expansion. Yeah, a mathematical scale. So the infinite Rabi mode here could be only derived from the cosine or the sine, the Fourier mode. Actually, I will show you here. This one is the original Hamiltonian, and we put the perturbation here, and so we could transform it into mass eigenstate, so it get an x. Next page. Next. Oh, yeah, yeah, just a shift. Yeah, the face here, five face here. Step function, if I change the perturbation into the form of state function, and then I could determine if phase is equal to zero. That means in the beginning the step function just like this, and then do this. But if I have the phase shift, maybe the step function will shift to left. So in the beginning, the step function will, yeah. Phase is determined by a cycle, right? A cycle of any periodical behavior. So the step function actually is periodical step function, up, up, down, and up, down. Yeah, 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 Yeah. Oh, yeah, 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 yeah. That's my meaning of phase here in this context. Uh, you mean in step is periodical step function? Yeah, yeah. Um, you mean the phase of the angle? Oh, you mean angle? Yeah, I define by one cycle. We usually use one cycle 0 to 2 pi. So in the step function case, I could define the maybe the wavelength, one periodical length. Yes. Okay, thank you, thank you. Okay, let me go back to the shift. Yeah, so in this context, we could observe the phase effect cannot occur in periodical step function, and the suppression effect cannot happen in step function too. So in in a kind of perspective, we could say maybe the step function is more fundamental in this neutrino parametric resonance system. Yeah, I have this little conclusion here. So here I will explain more about the step function, and this is not the periodical step function. I just try to use this figure to tell you another method to analyze the parametric behavior. Because in this right plot, we could observe an easy sinusoidal maybe density profile. So for analyzing the sine wave into this method, we should split it into many little step density profile. Then the mathematical form is like this. All the all the time evolution metric will multiply together orderly. Uh, and then here is the phase turn. The phase turn is coming from the Hamiltonian and the frequency. Yeah. So a little introduction for the second method. The second method is use this splitting viewpoint to deal with the sinusoidal condition. And actually, this method have been developed by Chernoff 30 years ago. However, he just used this method to deal with periodical step function because, as we can see, the result of this form is the multiplication of infinite thing. So they cannot apply this method to sinusoidal like this changing density profile because the multiplication may be complicated as they can imagine. So they just apply this method into periodical step function. But I try to apply the method into sinusoidal. And as we can guess, the result may be too complicated to analyze. So we use perturbation like this. This form is the probability. The probability is composed of 1, 2, 1, 2, 3 refers to the polymetry. Polymetry with the level 1 or X, and polymetry with level 2 or Y. Polymetry with level 3 Z. And this is the probability, transition probability. Because the 1 and 2, the polymetry is live in the off diagonal. So when the diagonal term equal to 0, that means the probability will achieve 1, achieve resonance. So actually, after doing the perturbation, I will get this complicated term. And the term here, the delta theta is the order. Because the theta means mixing angle here, the matter mixing angle. So the reason why we have many delta theta is because of the changing of the density profile. So the mixing angle will change with time or change with the space. However, if we ignore this delta theta, this leading order term, we just need to focus on the first term. The first term will be interesting because the phase here will be summed together. The phase term will be summed together. So if we try to find the resonance condition, that means this term should be 0. So sine summation phase should be 0. The condition is left. The summation of phi should be n pi. Oh, yeah. Right. Okay. X is a vector. Yeah, yeah. Sorry. So it's a arrow. Sorry. You mean this line? Yeah. This is time evolution operator. Yeah. Yeah. Okay. Oh, I'm sorry. X3 is not a vector. Is the component of X. The arrow the arrow here is an arrow. Yeah. It's the third component. Okay. So, yeah. I will explain here. The vector is coming from here, as we can see. The Hamiltonian, the time evolution is coming from this Hamiltonian, and the Hamiltonian could be described by polymetry. So the vector is coming from here. We use polymetry XYZ as the two-level metric basis. So we could get a vector n here. The n xyz refers to the component of polymetry. Yeah. N is vector. Yeah, n is x. Yeah, n is x. Yeah. Yeah. I'm sorry. Uh, yeah, x3 will be n3. Yeah. But actually, the vector x is after I multiply all the n here, n1, n2, n3 multiply together. So I could get the final vector x. Okay, thank you. Yeah. Actually, I do the perturb. I put it in the backup, but if I try to explain here, is as we can see. Okay. Um, okay. Backup slide. Okay. But this too much. Sorry. Let me try to explain here. The n the n is composed of the mixing angle, the matter mixing angle, right? mixing angle because the n is coming from the Hamiltonian here. So the perturbation is coming from the mixing angle, the delta theta. A matter mixing angle because the matter density profile is changing with this sinusoidal behavior. Yeah. So well, we could focus on this graph, the Hamiltonian 1, Hamiltonian 2 with different matter mixing angle. But I just consider the small or the nuance of the change of the density. So I have a delta theta, delta mixing angle. Yeah, this is the perturbation. Okay. So we first we ignore the perturbation term. We just focus on this term because when I do the mathematical derivation, I found all the phase term could be summed together in this sign. This is a coincidence. Really interesting. So the result told us when the resonance condition is when the summation of phase term equal to n pi, and this k is the frequency of fluctuating matter. So this is the resonance condition because x3, sorry, the arrow, x3 means diagonal term. So when the diagonal term equals to 0, that means all the element will transform completely into another state. So this is the more precise resonance frequency and depend on n. N is means 1 refers to first resonance, 2 refers to second resonance, and the C is the something constant here. Yeah. And then this is my numerical result. In this second resonance result, we could observe from this data when K is close to this red number, the probability will almost achieve resonance. So actually, the resonance frequency is not occurring in 1/2. It will be shift to this 0.00025. Yeah, it will be shift to that. So for the third resonance, we also found the phenomena here. The third resonance, the frequency, is not located at 1/3. 1/3 is close to this term. However, the probability is very small. But when it close to this value, the probability will achieve the largest one. But it cannot achieve 1 because of the suppression effect. And we have compared this numerical result. We have compared this numerical result with this theoretical result, and we found the error less than 1%. So that means this shift term have the confidence less than 1%. Yeah. So this is the shift of resonant frequency. Okay. Yeah. Uh, yeah. Yeah, if at the end, like the outline here, I will derive the general form, and then yeah, it's not relying perturbation theory, but because the general form is too complicated to derive, so the first we can do is do the perturbation and to prove shift of frequency. Yeah. Okay. And at the end, just a few slides because the general form is too complicated to be done some numerical thing. So this is the general form I try to derive, and actually the final form would look like this. And then the interesting point is here. This is the vector n multiply, or I say dot with polyvector. And then the order here could be 1, 2, 3, or to infinity. But the property, based on the property of polymetric, actually the regular could be observed here. That means if j equal to 1, it will be similar, the form will be similar when the j equal to 5 or 9. That means the cycle of this form is 1, 2, 3, 4, 1, 2, 3, 4. But the component will change to another value, but the vector form will be the same. This is the meaning of this general form. So I could extend this general form into this expression. So we could observe this is the first term. The first term, and this is the second term. We could observe the vector here is pure. And then if we consider the third term, the vector is here, and we should consider another vector y here. So this is the third term. And then we should consider the fourth term. The fourth term is too complicated to explain, but we just know they are the combination of different n vector here. They have some relation. The relation have n1, n2, n3, or another vector perpendicular to n1, to n3 here. Yeah, so this is the meaning of the general form. And we all could also express the general form in this form, and it will easily be done the numerical solution, because from the summation here is like many for loop. So I try to use many for loop to derive the general, to simulate the general form. Okay, so at the end, I would like to say the parametric resonance, or this behavior, is it could be it's like the pendulum, and the regular of pendulum is observed by him 400 or 500 years ago, and then he feel regular and is compared to the regular pulse, his pulse, and then he observed the regular of gravity is related to this thing. So actually, the parametric resonance has been analoged to this pendulum too by the previous paper. They say the neutrino parametric resonance is like if we can change the length of the pendulum, the length is changed with time, and change with time in a specific frequency. The pendulum will through the total the circle like resonance. This is the parametric resonance in another viewpoint. And I try to apply this viewpoint in graph. So consider the probability here. Here is x1, x2, x3, and x1 refers to x here. x3 refers to z here. So at the beginning, the n vector is composed of x and z. X means diagonal term, and x means off diagonal term. So this component means the off diagonal term, and this component means the diagonal term. So if we multiply more Hamiltonian into the unitary into the time evolution metric, we should consider more vector sum together and then more vector sum together. At the end, I found all the vectors sum together, the plot look like this, but I have no time to do the precise numerical result. But the naive guess is like the behavior is the sum of this vector. So we could say for more visual way, the resonance is happen when the sum of the vector will collapse into diagonal off diagonal term x here. So in another viewpoint, it's a little like the sum of the vector will be shorter and shorter and shorter and rotate. So in some condition, it will all collapse into the off diagonal term. So this is the picture. Yeah. So above is my physical interpretation, and then I try to write something in VPython. We could observe the V1 and V2 is like a mass eigenstate. So actually, V nu e and nu mu is the flavor space. So they get a mixing angle here. However, I use the slide means the matter is fluctuating. So that refers to the mixing angle is chained together. And I try to plot the behavior into this the same oscillating plot. Then we could observe the resonance is like if I move the slide into specific frequency, it would achieve resonance. So above is my argument in this context. At the end, I will do the conclusion. The conclusion is coming from my outline. And the first one is like the parametric resonance could occur in neutrino oscillation. This is obvious. And then the phase effect in self-interference. This effect is coming from the mixing of energy condition because the energy condition will be changed after we doing some basis transformation or the Lamar's method called corrotating wave approximation. And the third one, the asymmetry shape is the exact solution of interference term. We have proved it analytically. The interference term containing one symmetry term and another asymmetry term. And they also containing the phase term. So the phase could affect the shape of frequency response. And the fourth one, the shift of resonance frequency. We have analytically derived. We use the old metric method. The old method, we apply this old method with perturbation and derive the shift of resonance frequency. But like Professor Lin have mentioned, we could not just rely on perturbation. So in the general form, I believe we could derive the more precise the shift of resonance frequency. And at the end, the general form for me, it could be analog to the classical system, like the pendulum with the changing of length. So above is my conclusion. So for the acknowledgement, I really appreciate the help from Mengru and Boyan. And I have write something in the acknowledgement. I say if I could contribute to the field of physics, even though just a beam, instead of a beam of light from a bunch of electrons, that means the beam is like this. So in the research of master degree, I just like this beam with many pressure. And from this paper, the measurement of the internal force of the 6 Actually, the pressure is 100 times the atmosphere. Yes, it's very large pressure to do some chemical reaction, and then it could root in the soil and grow up together. So I feel I like a bean, and even though I cannot contribute something from a bunch of electrons, it could emit a beam of light. This is a laser. Yeah, so I really appreciate my advisors. And I also appreciate Martin and Professor Lin because actually the most important equation in my master paper is this form, the exact solution of the interference term. Actually, this equation was derived on Martin's course because I guess I was inspired by Martin's course and I just derived it. Yeah, I just derived it. So I really appreciate Martin's course. And for Professor Lin, I get some sense of symmetry in your name. So I figure out, oh, the form of symmetry and symmetry. Yeah, so I really appreciate all the committee and audience here. So above is my master oral explanation. Thank you everyone.